Good morning, everyone. So today is the last session of our uh, special session 12. So our first speaker for today is Dr. Amit Priyadarshi. Dr. Amit Priyadarshi is an associate professor of mathematics at the Indian Institute of Technology, Delhi. His research interests lie in fractal geometry and analysis. He has worked in areas such as fractal dimension, fractal interpolation, fractal transformation, and analysis on fractals. His research primarily focuses on theoretical aspects of fractal geometry while also contributing to its computational aspects. We warmly welcome you, sir, and thank you for joining us. Please proceed.
Okay, thank you very much. So first of all, I would like to thank the organizers for giving this opportunity to present a talk in this session. So today I am going to talk about some operator theoretic methods in estimating the Hausdorff dimension. So we all know that Hausdorff dimension is one central theme in fractal geometry, and estimating Hausdorff dimension is generally not an easy task. So Uh, in this talk, I'll talk about Hausdorff dimension of an IFS, iterated function system, and then we'll see mainly how like these operator theoretic approach using Perron-Frobenius operator and spectral radius can be used to estimate the Hausdorff dimension of attractors of iterated function systems. So let me start with some preliminaries. So first, briefly, I'll talk about Hausdorff measure and Hausdorff dimension. So to define Hausdorff dimension, we need a notion of Hausdorff measure. So this Hausdorff measure is something like similar to the Lebesgue measure that we all know. So, and this can be defined on a general metric space. So I take general metric space XD, and then we define first this HS delta for any non-negative S and for any delta positive. This is the infimum of summation of diameter of AK's raised to power S, where AK is a countable cover of A and diameter of each AK is less than delta. So this is called a delta cover of A, and we take the infimum over all such uh, delta covers, and then it can be shown that this HS delta is an outer measure, and if we look at if we vary delta, so as delta decreases, this HS delta will increase. So we can define HS of A as limit of HS delta of A, which is also equal to supremum of HS delta. This would be HS delta of A. So then it can be shown that this HS is a Borel measure, and this is called the S-dimensional Hausdorff measure. So we can see that if we take S equal to 1, and then the Hausdorff one-dimensional Hausdorff measure is same as the Lebesgue measure on R. So then using this Hausdorff measure, we define Hausdorff dimension. So Hausdorff dimension is that a unique number S naught such that for all S less than S naught, HS of A is infinity, and for S bigger than S naught, HS of A is equal to 0. So this is the value where the dimension goes from infinity to 0, and this is called the Hausdorff dimension of A, which is quite an important concept. So of course, we have the many properties of Hausdorff dimension, like this is monotonic, and then if we have a subset of Rn, then Hausdorff dimension is always between 0 and n. And for the usual sets we have, the Hausdorff dimension is same as the other notions of dimension. So let me now go to iterated function system. So first I'm talking about finite iterated function system. So if we have any complete metric space X, and suppose we have a finite number of contraction maps. So contraction means that distance between theta x, theta y is less than equal to a constant r times distance between x, y for all x and y, where this constant r is strictly less than 1. Right? So if we have any complete metric space and a finite number of contraction maps, then we call a non-empty compact set as attractor or invariant set for this IFS if A is equal to union of theta I of A. So the set A is made up of for this union of for images of A under these maps theta I. And using the Banach fixed point theorem, one can show that there is a unique attractor for any given IFS. So what we do is we take the Hausdorff metric on the set of all non-empty compact subsets of this X. And then if I am assuming this complete metric space so that the contraction mapping principle can be applied. So if we start with a complete metric space and then on the space of all the non-empty compact subset, the space is again complete with respect to the Hausdorff metric, and then we have a contraction map on that, and using that one proves. So these are the standard things, so I'm not going into the details. So maybe some examples. So the usual well-known fractals can be seen as attractor of some IFS. So for example, I think I did not put on the slide. So if we take the Cantor set, so we can take two contraction maps. One is x going to x by 3 and x going to 2/3 plus x by 3 on R. And then we can show that the Cantor set is the unique attractor of that IFS. So, and similarly, other fractals like Sierpinski cascade, Koch curve, those can be shown as attractor of an IFS. So let me also talk a little bit about infinite IFS. So here I assume that XD is a compact metric space and I is any countable set. And for every index small I in this countable set, we have a map, contraction map theta I such that this contraction C is less than 1, and we will also assume that the supremum of all these so here I'm saying that the contraction constant for each map is bounded from above by a constant C less than 1. So in this case also we can talk about attractor or the limit set of this IFS. So for that we look at all sequences I1, I2 and so on, all infinite sequences where these IIs are from the E set I, right? So these are called words and I is the alphabet set. And then for any omega in this I infinity, if we take any x in the space X and for any natural number n, we can define xn of omega to be the iterate theta I1, theta I2 composed with theta In of x. And then using that these maps are contraction, one can see that the distance between xn omega, xm omega, this goes to 0 as n and m goes to infinity. So that shows that this xn omega is a Cauchy sequence. And because the space is complete, this will converge to some. So this xn omega must converge to some point which I denote as x xi of x comma omega. And if x and y are two different points, then distance between xn omega and yn omega, this again goes to 0. So that means that the limit is independent of x, right? So this xi x omega is actually independent of x. So we define this to be pi of omega. So given any infinite sequence omega, we have a limit of theta I1 composed theta In of x. This does not depend on x. So I can take any point x and it will get a point in capital X. So then we consider the set of all these images pi omega. So this is called the coding map. Like for any word, I have a point in my space X. So this is called the limit set, and it can be easily seen that this is invariant. So that means that J is equal to union of theta I of J. And if the set I is finite, then this J must be compact. So in that case, it gives us the unique attractor of the finite IFS. Right. So this is all about a finite and countable IFS. Now we talk about similitude or similarity transformation. So if we have any metric space, a map theta is said to be a similitude if distance between theta x and theta y is some constant times distance between xy for every x and y. So that means that and we also want contraction map. So we will assume that this uh, ratio r is strictly less than 1. So if we have, suppose, a finite IFS where each theta I is a similarity transformation with some ratio, say Ri, then the attractor, this is called self-similar fractal, and its similarity dimension is given by the unique non-negative S, for which summation of Ri to the S is equal to 1. So again, some examples. So for the case of Cantor set, we have the two maps are actually similarity maps where R1 and R2 are both equal to 1 by 3. So similarity dimension will be given by 1 by 3 to the S plus 1 by 3 to the S equal to 1, which will give S equal to log 2 by log 3, which we also know is the Hausdorff dimension of the Cantor set. And similarly, if for other self-similar fractal, we can calculate this similarity dimension. If all Ri's are equal, then it is very easy to see what this similarity dimension is. Otherwise, also we can numerically compute the similarity dimension easily. So now we go to a generalization. So instead of taking similitude, we will define what is known as an infinitesimal similitude. So we assume that XD is a perfect metric space. Perfect means that every point is a limit point of X, so there should not be any isolated point. And a map theta from X to X is said to be an infinitesimal similitude at a point S in X if I take any two sequences, say Sk and Tk, where Sk is not equal to Tk for all k, and both these sequences approaches S in the limit. Then we look at the limit of this distance between theta of Sk and theta of Tk divided by distance between Sk Tk. And if this limit exists, and is independent of the chosen sequences SKTK, then we call this limit to be d theta of x, and this theta is said to be an infinitesimal similitude. So maybe here, because I have taken this map from x to x, so this d2 and d1 are same, the metric is same, but in general we can take from one metric space to another metric space, and then we can have different metrics d1 and d2 for x and y. So we call this an infinitesimal similitude if it is an infinitesimal similitude at each point in the space X. So let's see that this is a generalization of a similitude. If we have, suppose theta is a similitude, then in that case distance between theta sk theta tk is same as r times distance between sk and tk, so that cancels, and then this limit is clearly equal to r. So every similitude with similarity ratio r is an infinitesimal similitude with d theta of x is equal to r. We will also see this in another case later. So now to use this Perron-Frobenius operators, let me just recall the spectral radius of a bounded linear operator on a Banach space. So if we have T is a bounded linear operator on a Banach space X, then the spectral radius is given by this Gelfand formula, which is limit of norm of T raised to n. T raised to n means T composed with T with itself n times, and the nth root of this, right? The spectral radius is defined as supremum of mod lambda, where lambda is in the spectrum of T, and this nice formula gives a spectral radius in terms of the norm of these operators. So now let's look at some of the literature reviews. So in 1981, Hutchinson basically gave a general theorem about Hausdorff dimension of attractor of finite IFS on Euclidean space. So what he proved is that if we have, suppose these theta i's are contraction maps on Euclidean space Rn, and suppose these are similitude, and he assumed one disjointness condition, separation condition known as open set condition. So then in that case, he proved that the Hausdorff dimension of the self-similar fractal is equal to the similarity dimension, right? So this easily gives the Hausdorff dimension of self-similar sets like Cantor set, Koch curve, Sierpinski cascade, etc. very easily, because this similarity dimension is easy to compute. Of course, this open set condition and Euclidean space, these are important in his result. Right? He also proved something about the Hausdorff dimension of the invariant measure. But there are many examples where these maps are not similitudes. So one important class of examples is that if suppose we consider a set of all real numbers in, say, the unit interval, where if I write the continued fraction expansion, then I know that any number can be written in continued fraction expansion where the digits are a natural number. So suppose I restrict the digit to be a subset of natural numbers. So I don't take all the natural numbers at the digit, but suppose I take only some finite subset, or one can allow infinite subsets also, and then consider that set, right? So then one may ask, like, what is the Hausdorff dimension of those sets, right? So of course this set can be seen as attractor of IFS, so by taking the map x going to 1 by x plus n, where n is a natural number, and then if I have any subsets, I can restrict this n to be that subset, and then the attractor of this IFS will be exactly this set, right? But these maps are not similarity maps, so therefore Hutchinson's result is not applicable here. So this continued fraction thing, it was studied by many people, and people estimated the Hausdorff dimension to high accuracy, mainly results by Jenkinson and Polycott. So they gave efficient algorithms to estimate the Hausdorff dimension of these numbers where continued fraction expansion has digits in some finite subset of natural number. So now, because we want to use this operator theoretic method, let me define what is known as Perron-Frobenius operator. So we'll have X is any compact space, and C of X, suppose C of X denote the space of all continuous real valued functions on X, and here we can define the sup norm. So then this becomes a Banach space. So Cx is the Banach space of this continuous real valued function on X. And then we define, given any IFS, I define the so-called Perron-Frobenius operator. So this is defined for every sigma which is positive. So for any real number sigma, positive real number sigma, we define L sigma from C of X to C of X, where this is defined if I have any continuous real valued function f in Cx, then the image should also be in C of X. So L sigma f at any x is defined as summation of d theta I x raised to power sigma and f composed with theta I of x. So if we look at this Perron-Frobenius operator, and then this actually he helps us to give this. So the main theorem is this, that the Hausdorff dimension of the limit set is the unique value of sigma for which the spectral radius of L sigma. Now these are all operators on a Banach space. So we ask what is the spectral radius of L sigma, and the unique value where the spectral radius is equal to 1, that sigma gives us the Hausdorff dimension. Of course, there are some assumptions required. Like even in the Hutchinson's result, we require open set condition. So we can't expect that without any assumption, this result will be true. So let me also say that suppose these maps are similitude. So in the Hutchinson setting, this d theta ix we saw is Ri. So in that case, this is just Ri to the sigma and f of theta ix. And in that case, the spectral radius of L sigma can be seen to be just summation of Ri to the sigma. So what this result is saying is that spectral radius is equal to 1, that is same as summation Ri to the sigma is equal to 1, which means that sigma is the similarity dimension. So our result, this one, generalizes the case of similitude. But here, so I am assuming these theta i's are infinitesimal similitude, so that I can talk about this d theta ix. So the important point is that this result is very general. I am not assuming space to be Euclidean space. This is on a general. If we have an infinite IFS, we assume the space to be compact. Otherwise, for finite IFS, only complete metric space is enough, and then this gives us the Hausdorff dimension in terms of spectral radius of this family of Perron-Frobenius operators. So after this result, later Richard Falk and Roger Nussbaum, through a series of paper, in the end I'll show the references, they use this Perron-Frobenius operator method to obtain efficient algorithm to compute the Hausdorff dimension to high accuracies. Right. So if we see this one, it gives us a general theorem which tells what is the Hausdorff dimension. But for practical purposes, estimating this Hausdorff dimension, estimating the spectral radius of L sigma may not be easy, because this is on infinite dimensional Banach space. So what they did is that in many cases they showed that they can get algorithm which can help us to compute this spectral radius and hence the Hausdorff dimension to high accuracy. Let me also mention that this spectral radius of L sigma, this satisfies if I vary sigma, then as sigma increases, this is strictly decreasing, and if sigma tends to infinity, this will go to 0. So this is like a strictly decreasing function, and it is. So if suppose it is less than 1 at some point, then that gives us an upper bound for the Hausdorff dimension. So in practice, what we do is that we try to compute this RL sigma for some value of sigma. If it is bigger than 1, then that gives us a lower bound for Hausdorff dimension. And if it becomes less than 1, then we get an upper bound. So to get a good estimate for the Hausdorff dimension, we can keep increasing sigma till we get this R L sigma is bigger than 1 to get better and better lower bound. And similarly, we will keep reducing this sigma for which the spectral radius is less than 1, and that will give us better and better upper bound. Okay, so also in a recent paper, Nussbaum gave some elementary comparison theorem. So basically, let me tell you what this is. So I talked about this example of continued fractions. So suppose I take continued fractions where I allow digits to be some subset f1 of natural number. And if we take another subset f2, then if I look at the Hausdorff dimension of the corresponding sets, then can I tell like which one is bigger? For example, if you take, say, digits are 1 and 2, right? So you look at all real numbers where the continued fraction expansion has digits only 1 and 2. And suppose you take the digits to be 1 and 3, then which one is bigger? Or if you take, say, 1 and 3 and 2 and 4, right? So in the first case where like I take 1 and 2 and 1 and 3, it is not that difficult to, if you increase one of the digit, then the Hausdorff dimension will decrease. But suppose I take 1, 3 and 2, 4, then which one is bigger? So of course one has algorithms to estimate the Hausdorff dimension. So if you calculate the dimensions, then you can see which one is bigger. But the main point of this result is that without actually computing the dimension, one can prove that Hausdorff dimension of one set of continued fraction is greater than the other set by using this spectral radius method. So now let me come to one example. So this is a set of complex continued fractions. So we talked about real continued fraction. Now one can talk about, suppose this J is set of all complex continued fractions of the form 1 over B1 plus 1 over, so this notation means that we have 1 over and then B1 plus 1 over B2 plus and so on, just like we write in the continued fraction. So where these B1, B2, these are from this set M plus Ni, where M is natural number and N is Z. Right? So this is a countable set. So I look at all complex numbers which can be written like this. So this example was first studied in 1983 by Gardner and Mauldin, and they proved that the Hausdorff dimension of J is strictly between 1 and 2. So that itself, of course, it is a subset of R2. So the dimension cannot be more than 2, and also it can be easily seen that it cannot be less than 1. But proving that it is strictly bigger than 1 and less than 2, that itself was a non-trivial result. And later in 1996, Mauldin and Urbanski, they proved that the Hausdorff dimension of this set lies between two numbers, 1.2484 and 1.9, right? So still you can see that the gap is too much, right? So the lower bound and upper bound, we don't have a very good estimate for the Hausdorff dimension, right? So what we'll see in this talk, that using the Perron-Frobenius operators, one can estimate the Hausdorff dimension much better. So for that, we first look at this set as invariant set, limit set of an IFS. So we look at the closed disk of radius half centered at half in the complex plane. And we look at these maps, B going to 1 by Z plus B, where B is in this set I. And then it can be seen that this theta B maps this closed disk X into itself for every B. So, and also J is precisely the limit set for infinite IFS given by this theta B. Right? So this is analogous to the real continued fraction case. There also we have the same kind of maps. Here only thing, these are all on the complex plane. So now, also in this case, these theta b's are infinitesimal similitude with d theta b of z is nothing but the absolute value of theta prime z, where this theta prime denotes the derivative of this. Right? So this is the Perron-Frobenius operator for this. For any sigma positive, we define this. And using our theorem, we get that the Hausdorff dimension of the set J is the unique value sigma for which the spectral radius of L sigma is equal to 1. Right? So now the thing is how to estimate this sigma. So, like I said, that if I get for some sigma, the spectral radius is bigger than 1, then that will give a lower bound. And if I can get this is less than 1, then that gives an upper bound for Hausdorff dimension. So, yeah, so I have mentioned here that because this is strictly decreasing continuous function of sigma, the if the spectral radius is bigger than 1, that gives a lower bound. So using this, and one more thing, that if I look at instead of L sigma, I look at the composition of this L sigma k times, then by the Gelfand theorem for the spectral radius, it is easy to see that the spectral radius of L sigma raised to power k is nothing but the kth power of spectral radius of L sigma. And we are interested in the value where the spectral radius of L sigma is equal to 1. So that will be same as the value where spectral radius of L sigma raised to k is equal to 1. So instead of using L sigma, we can look at L sigma raised to k for any positive integer k. So for practical purpose, this is important, because if we use L sigma, spectral radius of L sigma, to estimate the Hausdorff dimension, we may not get very good bounds. So instead, we go for higher iterates. So of course, using the formula for L sigma, if I take L sigma to the k of f, this can be written as summation of theta omega prime z mod raised to power sigma f of theta omega of z, where omega is the any finite sequence b1, b2, bk in I to the k. So, and theta omega of z is the composition, theta b1 composed theta b2 up to theta bk of z. So then, because theta b of z was 1 by z plus b, so this is theta omega is a finite composition of Mobius transformation. So theta omega is also a Mobius transformation. So, and in fact, one can get that theta omega of z is equal to this pk minus 1 omega z plus pk omega divided by qk omega minus 1 omega z plus. So we are writing it as az plus b by cz plus d. And because this is taking composition up to k, so that will depend on k and omega. And we can get these recurrence relation for pks and qks. So that means that for any of this b1, b2, bk, one can get a formula for theta omega of z, and then we can calculate its derivative. So here is the formula for the derivative will come out to be this. And initially we had the disk which is centered at half and radius half. So in general, if I have any Mobius transformation and D is any closed disk centered at Z naught with radius R naught, then the image of this under the Mobius transformation, this will again be a closed disk with center given by this formula and radius this, if my minus d by c is not in D. So we know from complex analysis that Mobius transformation maps lines and circles to lines and circles. So using that, we can get these formulas and yeah. So then the next lemma is applying this to our case, where if I have any omega and then theta omega of x we want to see. So because of infinite dimensional Banach space, estimating a spectral radius is difficult. So for this example, we can think of like reducing it to a spectral radius of a matrix. So how that can be done? So what we do is that first of all, instead of taking the infinite set I, we take I tilde to be any finite subset. And then we look at uh, x tilde equal to union of theta omega of x, where omega is in I tilde to the k. So now I am not taking infinite IFS, only like reducing it to fine, restricting to any finite subset. And then if I look at this, the spectral radius was sum over all omega in Ik, but now I'm taking only a finite subset of this. So of course this has to be bigger than equal to if I take over this, because all are non-negative things. So we get this, and then we can find the minimum value of this derivative of theta omega prime z on that disk where this uh, z belongs to the closed disk of radius half centered at half. So this again, because I know formula for this theta omega prime z, so one can get the minimum value. So we are again replacing this by a constant. So this is greater than equal to this, and that way we can reduce this to a matrix. So then we will take a matrix where the entries are this a omega omega prime raised to sigma. So this can be computed, and then we look at this matrix whose size is whatever size of I tilde I have taken raised to power k cross that. Right? So, and then the spectral radius of this L sigma raised to k is greater than or equal to the spectral radius of A sigma, where A sigma is this positive matrix. Right? So that spectral radius can be estimated using like MATLAB or any other uh, software. And if we can get a lower estimate for spectral radius, which is bigger than 1 for some sigma naught, then that gives a lower bound for the Hausdorff dimension. Right? So this, like in one paper did, uh, took only k equal to 2, so second iterate, and I tilde to be m plus ni, where m is from 1 to 9 and n is from minus 9 to 9. And using MATLAB, we get, so this already becomes a matrix of size 29,241. And using this, it was shown that the spectral radius, uh, yeah, for sigma naught equal to 1.825, the spectral radius is bigger than 1, and that gives the lower bound for the Hausdorff dimension as 1.825. And if one takes a bigger k or I tilde to be a bigger set, then one can get a better lower bound for this. Right? So this was like showing that how we use this to to get at least a lower bound for this. So for finite IFS, it is not a problem. One can get both lower and upper bound. For infinite, getting an upper bound is a little challenging, but getting lower bound, one can use this technique. And uh, let me mention, so after this work was done, you see that this lower bound 1.825 is much better than the earlier best known lower bound, which was 1.28 something. So this already gave much better. And later, like I mentioned, Falk and Nussbaum, they obtained efficient algorithms to estimate this spectral radius. So using that, actually, they in another paper found the Hausdorff dimension of this complex continued fraction example up to, I think, 3 decimal places. So the actual value they proved is 1.85 something. So this because in this paper only like lower bound was obtained, upper bound was not obtained, but they got both lower and upper bound and showed that the Hausdorff dimension uh, can be computed up to 3 decimal places using their result. Okay. And yes, so let me then tell some of the references. So first one is Falconer's book on fractal geometry. And this, I said some papers by Falk and Nussbaum. So in 2018, this paper in Journal Fractal Geometry, where they give a new approach to numerical computation of Hausdorff dimension and applications in R. So for the continued fraction examples, for example, one can use this to do. And then in the same year, in this paper, a new approach to numerical computation of Hausdorff dimension of iterated function system and application to complex continued fractions. So in this paper, they found an estimate for the Hausdorff dimension for the complex continued example that we just discussed. And then another paper in Journal Fractal Geometry in 2022, they again gave some approach to numerical computation of Hausdorff dimension, higher order method. So even like higher accuracies one can get. This was Gardner and Mauldin's first paper where they introduced this example of complex continued fraction, and Mauldin Urbansky's paper where they obtained lower and upper bound. This is the paper that I was saying that if you have two different subsets F1 and F2, how to compare the Hausdorff dimension of the numbers given by the continued fraction expansion with digits F1 and F2. So this appeared in Contemporary Maths AMS. And this was the paper where all these things were developed for the first time using the Perron-Frobenius operator. And in this paper in 2017, the lower bound that I gave the detail, like how it was obtained. So thank you. And if any questions, I'll be happy to take.
Yes, thank you, Dr. Amit. I will now stop the recording and then